So next speaker is Farzam Toudeh-Fallah from Ciena. He's their R&D director of quantum communications, and he will take us along the road towards ultra long haul quantum communications. So very curious about it.
Thank you, Mr. Chairman. Good morning. I'm Farzam Toudeh-Fallah, R&D director, quantum communications at Ciena. What I'm going to discuss in this presentation is the challenges associated with ultra-long-haul quantum-secured optical channels, establishing those channels in real-world operational environments, and what Ciena R&D is doing in terms of addressing those challenges. So first, I'm going to define the problem, what problem we are trying to address, and then I'll discuss two distinct approaches Ciena is taking towards addressing this problem, i.e. terrestrial and satellite-based. Now, in terms of the problem statement, so today we have these capability to establish quantum secure channels at the metropolitan scale, as depicted in this figure from OFC demo that we conducted. For instance, you can see, for an example, we have the Ciena Wave server that is coupled with the Toshiba QKD device, and using this combination, this Wave server was able to receive the keys and establish 800 gigabits per second quantum secure channel at the OTN layer, at the optical layer. Also, we paired up another Ciena product, Ciena 8140, which is a routing and switching product. We paired it up with an ID Quantique QKD system, and using this combination, the 8140 was able to establish 400 gigabits per second quantum secure channel at the MACsec layer. We took that channel and passed it into the Wave server, which multiplexed it into that 800 gigabits per second OTN-sec quantum secure channel and sent it to the other side of the exhibition floor, where the reverse process took place and the secure channel was recovered. So this capability is available today for deployment at a metropolitan scale. We're talking about 100 kilometers or so. Now, the other thing that we demoed was the trusted node, the concept of trusted node by basically placing two QKD devices back to back. Now, in terms of extending the reach of quantum secure channel, obviously it is limited not by the optical channel, but by the quantum channel. And in order to extend that, trusted node is one option. Now, some customers are happy with trusted node, but some are not, because in the trusted node, as soon as the session key is converted from quantum to digital in order to be passed between the two back-to-back QKD devices, right at that moment, there is a point of vulnerability. So it depends on the customers. Some customers are happy with this, but some that they need end-to-end quantum secure channel, no trusted nodes in between. So for those customers, we are basically conducting research in establishing this long-distance quantum secure channel. Now, let me just clarify, by long distance, what I'm referring to is not a couple of 100 kilometers, no. What I'm talking about is thousands of kilometers, because that's the real world channels that we have deployed, and I'm going to talk about it later on, and we want to quantum secure those channels. So in order to do that, the first step we took was basically coming up with a series of requirements for quantum repeaters that could be deployed in a real-world operational environment. These four words, real-world operational environments, basically constitute the foundation of my talk. So you'll see during my talk, I will present you with numbers and data from real world that we have collected that back up what I'm talking about here. So first, let's take a look at an optical communication link that we are trying to quantum secure. In the long-distance optical communication link, we have two sites, site A and site B, that might be thousands of kilometers apart. We divide the distance into shorter spans. Each span is somewhere around 80 to 100 kilometers, and each span is connected to the next via an amplifier. These amplifiers are located in sites called ILA, stands for inline amplification site. Now, the first requirement, and first and foremost requirement that you're placing on basically establishing quantum secure channels long distance is the coexistence. So we are calling for coexistence of quantum and optical data channels on the same infrastructure that is available today. The reason is that the network operators are not going to build a brand new network just for the quantum network. This is not how it's going to work. It's not economically viable. So we have to come up with a solution that is deployable on what is available today. This would have two major implications. Number one, in terms of the fiber, we are calling for multiplexing the optical data channel and its associated quantum channel on the same fiber. Since the data channels are occupying C and already L, C plus L bands, there's no place for quantum channel there. Our recommendation is to launch the quantum channel on the O band, so we have around 200 nanometer guard band to protect against the Raman scattering coming from the optical data channels. So that's the first major implication. The second one is that these quantum repeaters must be placed in the same ILA sites that are hosting today's optical amplifiers. Okay. Now, these ILA sites, they're spread across the world. They could be in the middle of nowhere. It could be in a desert in Texas or in Australia. So they are usually, in terms of the size-wise, they are very small, 10 by 15 feet. And they are very, very limited in terms of the power and space they can provide to the telecom equipment. So we are dealing with the very harsh conditions that for the quantum repeaters. So now let's take a look at another set of data from real-world environment. What you're looking at is an example of a long-distance optical communication link between New York and Chicago. In terms fiber-wise, it's approximately 2,600 kilometers of fiber, and it consists of 31 ILA sites. Okay. Now, if we take a look at the loss per span at O-band, because again, we are recommending to launch the quantum channel on O-band. If we take a look at O-band loss, we see that on some spans, it can exceed 42 dB. So that's the real-world environment that quantum repeaters must be deployed. So based on all this, we at Ciena have come up with a series of recommendations for the deployment of the quantum communication channels in real-world environments. From the fiber optic perspective, again, we are recommending the operation in coexistence mode, which means quantum and optical data channels must be multiplexed on the same fiber. No dedicated fiber for quantum channels. Also, all degradation factors that are present in real world must be taken into account when we run analysis on the behavior of the quantum channel. In terms of the quantum repeaters, the first and foremost requirement based on what I just showed you now, we are calling for support for at least 45 dB link loss between the repeaters. So I'm talking about the spacing between the repeaters, 45 dB loss tolerance. The second one is absolutely no dedicated site for quantum channels. I'm going to discuss this later on. Some models basically require a third site between the two quantum repeaters. That's not going to work. The third one is the extreme limitation in power and space because of the ILA sites, and we have some numbers for that. And the last but not least is absolutely no cryogenic environment. You cannot expect any cryogenic environment in those tiny ILA sites in the middle of nowhere. And we are recommending at least 45 degrees centigrade ambient temperature tolerance for quantum repeaters. So these are the set of requirements. Now that I have defined the problem and the set of requirements that we're dealing with, let's talk about what Ciena is doing in terms of our approach to address this problem. We're taking two different approaches. The first one is terrestrial, I'm going to talk about here. So this is Ciena's vision towards establishing large-scale quantum optical networks. These networks will be able to support end-to-end quantum secure channels. So the distance between these end users, end nodes could be thousands of kilometers, but the goal is to establish quantum secure channel without any trusted nodes. So in order to do so, based on what I discussed, first, in this vision, the quantum and optical data channels are launched into the same fiber, multiplexed. Once they hit one of these devices that we call quantum optical repeater system, or QRS, the quantum and optical data channels will be demultiplexed. The optical channel will be routed over an optical element, and the quantum channel will be routed over a quantum repeater. Now, the optical element could be a ROADM, amplifier, or switch. At Ciena, we've been developing them for decades, so no problem on the optical side. Obviously, the question mark is on the quantum side. So, this is the model that we are considering in our analysis on the quantum channel. So my focus from now on will be purely on the quantum channel. So in terms of the quantum channel, the model that we are working on is entanglement distribution based. So in this model, again, we have two sites, site A and site B might be thousands of kilometers apart. We break it down into shorter spans. Each span somewhere between 80 to 100 kilometers. And each span is connected to the next via a quantum repeater specified with the letter psi. Now, you have noticed that I've already specified one of our major requirements, 45 dB loss tolerance between the two quantum repeaters, okay? So, in this model, first, each quantum repeater establishes entanglement, shares entanglement with its own neighbors, left, right and left. Once this is done, and for all quantum repeaters on the link, then all quantum repeaters go through a process known as entanglement swapping. Once the entanglement swapping process is complete, at that point, site A will be in entanglement with site B. Please notice that when this process started, site A was not in entanglement with site B. Once the entanglement between site A and site B is established, then we can utilize quantum teleportation to transport a quantum state, an unknown quantum state, from site A to site B. So I think you might be familiar with quantum teleportation, which is a major property of quantum communication. In this process, the unknown quantum state that needs to be transferred from site A to site B basically disappears in site A and appears in site B. So this is a general quantum communication link, long distance, regardless of the application. It could be used for any application. You know, it could be QKD, transferring, you know, the QKD quantum data. It could be for interconnecting quantum computers, interconnecting quantum sensors, whatever that is. This is a general discussion here. But since our focus at this point is on quantum secure channels, in other words, the application is QKD, we can also use some native QKD protocols that are entanglement-based, such as E91 or BBM92. Now, we are very well aware of the challenges that this methodology faces, including quantum memories with long coherence time, achieving high coupling efficiency, bosonic fermionic coupling efficiencies, and so on, achieving high fidelities, and achieving high entanglement generation rates. So, we are considering all these parameters into the model that we are basically developing. So at this point, our approach towards quantum repeaters and the vision that I talked about is a a top-down approach. So we are first trying to address a major fundamental question. Which quantum repeater model would have the capability to be deployed in real-world operational environment? That's a major question. Based on the set of requirements that I talked about, and we have collected from the real-world environment. That's a major question that we are trying to address. In order to do so, we're going to model this link using a simulator that we have and into a real-world link. What is that real-world link? That real-world link is a 6,000-kilometer New York-San Francisco link that basically has Ciena devices. Ciena already has DWDM devices deployed on that link. So we have collected all the data on this link. We know exactly what the data is. So we're going to utilize that data and the quantum repeater model, the quantum communication link model that I just talked about. We're going to combine them into a simulator, okay? We're going to run the simulation, and we're going to try different quantum repeater models to see which one would come out on top, okay, that can meet our requirements. So at this point, this is where we are. Once we have the answer, then at that point, we can sit down and talk about, okay, developing hardware or developing any quantum repeaters, anything. But at this point, no development, none. We're just trying to address a fundamental question. That's it. So there's no hype. There is no. It's all based on real data, real world numbers that I just presented. So let me show you now. You might say, wait a minute. These are engineering discussions. Now we are at the earliest stages of quantum repeaters. So this is just research, scientific. Isn't it too early? I would argue against that, and I'll give you some examples. So based on the analysis that we have run so far, based on what I discussed so far, these are some examples of quantum repeaters that already researchers are working today, and we're going to reject that. There's no way that these models are going to meet our requirements for real-world environment. The first one is known as one-way quantum repeaters. So in these repeaters, the idea is that to use quantum error correction per repeater to basically compensate for both link loss and operational error at the repeater. Okay, in theory, it looks very nice. There's no need for quantum memories. There's no need for two-way classical communication between quantum repeaters and so on. Very nice. But in reality, there is a major issue with this concept, and that is the 3 dB link loss tolerance thresholds. So because these quantum repeaters, these models, the one-way quantum repeaters are based on quantum error correction, if you take a look at the fundamentals of quantum error correction, it is limited by 3 dB link loss tolerance. So let's go back to the reality. The reality is calling for 45 dB link tolerance, right? So 3 dB is ridiculous. Out of the question, rejected. The second one is known as the mid-in-the-middle model. So in this model, we have a BSA site in the middle between the two quantum repeater, and basically what it does is that it conducts the Bell state analysis on the two photons that are coming in from the two repeaters, okay? Again, we reject this, and the answer is very simple. Based on what I discussed, it requires a third site. No third site. It's going to be just two quantum repeaters and no third site. The third model that we reject is midpoint source model. In this model, we have an entangled pair source in the middle that sends basically entangled photons to the two quantum repeaters to basically conduct, establish entanglement. Again, we reject it because it requires a third site. So you can see right off the bat, these models we reject these models for real-world environment. Yeah, they might work very nice in the lab or you're publishing a paper, but in reality, no, they're not going to work. So this is where we are standing with regard to terrestrial. But in parallel, we are also pursuing another path, which is satellite-based. So why we are pursuing satellite-based? That's because mainly we are looking at them for quantum securing submarine cables. So you see, submarine cables carry somewhere around 99% of the intercontinental communication traffic. So they are extremely vital to the world economy and commerce. So the question is, how can we quantum secure these submarine cables? Now, these cables in length, I'm talking about just a single segment, they can run up to 16,000 kilometers. So, and we recently announced that our modems can launch massive amount of data channels. For instance, on one of these cables that connects US to Singapore, that's 16,500 kilometers. So let's think about this. We have these massive data channels that are carried by these submarine cables. And the question is, how can we quantum secure this? We don't believe that even if the quantum repeaters are developed, not anytime soon, but when they are developed, they could be deployed on such massive distances, 16,500 kilometers at the ocean depth. So That's why specifically for this problem, we're looking into satellites. Now, in terms of the satellites, there are two different models. The first model is the trusted satellite model. In this model, a satellite in space establishes a quantum channel with the first ground station, and basically using QKD methodology, it generates a mutual keys between itself and the ground station, moves over the second one, establishes quantum channel, and basically transfers that key to the second ground station. At this point, the two ground stations will have the same QKD-generated key, and they can use that shared secret key to quantum secure an optical channel over the fiber that connects the two ground stations. So this model is called trusted satellite model because one has to trust the satellite. The satellite is aware of the key, okay? So if you can trust the satellite, this model is okay, and there is no limit as to how far apart the two quantum ground stations could be. They could be thousands of kilometers apart, you know. Now, in contrast to this, some people might say, well, I don't even trust the satellite. So I need a model that I can proceed with, a satellite that I can trust, okay? For those folks, there is a second model, and it's called entanglement-based model. So in this model, the satellite is nothing but just a dumb platform in space. All it does is just generates photon pairs and send them to the two ground stations. Once they receive those photon pairs, they establish entanglement between themselves, and using this, they can establish quantum secure channel over a fiber that connects them. Okay, so we are basically conducting analysis on both these models, so that's theoretical analysis, but experimental-wise, we are engaged in the quantum encryption and science satellite, or KeySat project. This is a 5-year research project sponsored by the Canadian Space Agency and is administered by the Institute for Quantum Computing, IQC, at the University of Waterloo. Ciena is a member of a consortium that is engaged in this project, and as a member, each member of the consortium has a specific role to play. As a member of the consortium, Ciena's role is very well defined. Our role is to establish quantum secure channels between the two quantum ground stations. So in order to do so, we will deploy our wave server platform that I just talked about, and we're going to deploy them in the two quantum ground stations. And then the wave server, as depicted in this figure, the wave server will establish an Etsy API channel with the quantum transmitter receiver box. That box is in contact with the satellite, and basically in communication with the satellite generates the keys for the wave servers. Once the two wave servers on two ground stations receive the same key, they can use that key to establish quantum secure channel over the fibers between them. Okay, so we have two main objectives. I'm going to wrap up by just talking about two main objectives here. Our first objective in our engagement in this satellite is that we want to understand experimentally. That's very important. There are lots of papers out there, theoretical calculation, but experimentally, we want to understand exactly how we can interface with the satellite and receive the keys and establish quantum secure channels, okay? So during this 5-year research project, we're going to collect the data. The reason I'm emphasizing on that, because when our, let's say, wave server system interfaces with commercial devices such as ID Quantique or Toshiba, we know exactly what we're expecting. The key generation rate is almost constant. It is a stable environment. But when we interface with the satellite, we don't know. It's an unknown environment. So for instance, if a satellite shows up over a ground station and there's too much turbulence, the key generation rate will go down dramatically. Now, having said that, one member of our consortium is just responsible to develop adaptive optics to compensate for the turbulence in the atmosphere. Even worse, what if the satellite shows up over a ground station and is completely cloud covered? In that scenario, it cannot even establish a quantum channel with the satellite, with the ground station it has to pass. So you see, the interface with the satellite will be a stochastic one. We don't know how it is, so we try to collect data and make a decision. So that's technological. Now, suppose it turns out that technologically, yeah, it's okay, we can work with the satellite, and we can adjust with the satellite behavior. Then the question is, from commercial point of view, is it viable? How much it's going to cost to build, launch, and control the satellite? Who is going to operate the satellite? Once we have all these questions as a result of this 5-year research project, and if it makes sense, then in that case, we can sit down and offer the solution to our customers. So with that, I'm going to wrap it up, and thank you so much for your attention.